Hi everyone, my name is Chandra Nikhil, and today I'll be presenting to you on the prediction of credit card approval project in the predictive modeling subject of OPM 5604. Sampling, exploring, modifying, modeling, and assessing SEMA. I'll be using the sequential methods to build machine learning models. This phase uses various analytics tools to determine the best model for predicting outcomes. Now coming to the business problem. With whatever is presented on screen, at present with the development of machine learning algorithms, more predictive methods such as boosting, random forest, etc. has been introduced into credit card scoring. However, these methods often need better transparency. It may be difficult to give customers and regulators a reason for rejection or acceptance. As more and more people started to rely on banks to take out loans, banks need to be increasingly more accurate in determining who gets those loans. Banks have resources that they allocate for loan approvals, and only selected loans can be approved because of the limited cash supply. However, there needs to be a method of absolute determination for the banks to be sure of whether the loan will be paid back. Banks suffer huge losses when people don't pay back the bulk of the loan, and it is challenging to predict the possibility of such a case. The risk associated with deciding on loan approval is immense, so we try to reduce this risk factor. My model helps the banks predict whether a particular customer should be given a loan based on information about the customer. My model therefore tries to minimize the risk as much as possible. The source of the dataset chosen for this problem statement is from Kaggle. The goal of the project is simple: the approval for good applicants and rejection, especially for bad applicants, which is of high importance to the banks to minimize the risk factor. There are 25,128 rows in my dataset with 21 variables, including essential predictors such as total income, family size, job type, age, experience, etc., that are possible determinants for credit card approval for an applicant. The target variable is status, and as shown above, the summary stats for some of the important columns, such as the frequencies of male and female applicants. As you can see, the female applicants are significantly higher than the male applicants, and the total income of an average applicant is about $19,436, and the total family members per each family is about 3 members, and the average applicant age is about 40 years, and the number of years, which is the experience of an applicant, is averagely 8 years. And we can also see the range of bad debt and good debt. While bad debt ranges from 0 to 49, the good debt totals from 1 to 61. Now let's look into the significant variable in the dataset, the target variable status, which talks about the applicants who were rejected or approved, which is shown in the binary category, where 0 meant rejections and 1 meant approvals. Something interesting about is the clear imbalance in the data. As you can see, there are only 121 applicants who are rejected, whereas there are about 25,000 people who are approved. Such imbalanced data can be resolved using techniques such as stratified split balance to resolve such problems. Let's understand a bit about the data before we dive into modeling it. The above first visualization of three important predictors that I feel are namely income range, income type, that is the source of income such as commercial associates, pensioner, state servant, student, and working professionals, versus the percentage of some good debt and some bad debt for them. While good debt is majorly observed in all categories, it is interesting to see how the lowest income bin in pensioners and other income ranges too in them have the highest sum of bad debt. State servants and students have negligibly no bad debt when compared to the other categories. Now to confirm our intuition from the first visualization, here is another stacked graph for the same predictors versus our target variable status for approval and rejection. It is evident how bad debt directly affects the approval status, and as we can only observe significant rejections in the pensioner's income type, whereas the other income types have 0 to no rejections. Now, moving on to the next step of data exploration, finding outliers, missing values, which are precursor for data preprocessing, that is variable reduction. We can observe a few outliers in the numerical variables, that is total income and total bad debt. But upon closer inspection, these outliers are not changed or removed since they make sense and don't categorize under human errors. And they provide some valuable data points. There is only a single category in this column called own mobile phones, which is redundant, essentially being no essentially unable to draw any insights, and it is finally excluded. And also the column known as the applicant ID, which acts as an row identifier, which consists of all unique values and which will not be included in our modeling process. And luckily, we have no missing values to deal with in our dataset. Further into the variable reduction process, we have used correlation matrix to see the correlation between the variables in the dataset. There is a zero point 0.9 correlation, which is very strong positive correlation observed between total children and family members, which makes sense, right? As the total number of family members includes the children, as it is very obvious that this data is redundant and children is a subset of family. I have decided to exclude the children row entirely. And as observed from the rest of the matrix, there is no strong correlation, neither positive nor negative, that is observed between the various features, which is a good thing, as it ensures that the information in the dataset is not redundant and all the features are important. Further into the data preprocessing, it is important to check for skewness in any of the data columns, as it might introduce bias into our modeling. The distribution of data for all the numerical rows has been examined, and the skewness has been observed for total income and years of working. The skewness was thus reduced using Shash transformation, which is depicted above. Data reduction process, PCA analysis, nothing but principal component analysis. It helps us to reduce dimensionality of the data. But since we already have very less variables, I'm just using this to check how much redundant data is present in the data point, which talks about the same, which gives us the same insights. In the percent, we can see the total amount of data being captured using the 12 principal components. If we want to capture about 94% of the data, we're just reducing two variables and taking until 10 of the principal components. So I just decided to not to go with the principal component analysis, which is also hard to explain in nature in the modeling and final result process. Entering into the model building process. The most important problem in our data, that is the target variable imbalance. Here we are using the stratified split add-in in JMP to balance the inputs in training and validation sets. I'm using the thumb rule proportions of 60% training, 20% validation, and 20% testing, with the focal group being the one in less proportion, that is 0, or the rejections. Using the model screening feature in JMP, I ran the simulation for all the models to predict my target variable. Above, you can find a summary stats for the same. AUC must be near to 1 and misclassification rate should be near to 0, and RASC must also be low to call a model a good predictor. Some of the good models observed were bootstrap forest, boosted tree, and the area under the graph can be observed on the right in the ASU graph. Let's see more about the first optimal model, bootstrap forest. Confusion matrix can be observed above, and something important to notice is how a prediction of interest, I predicted 1 or approved, but an actual 0 or rejected is actually 0. It is amazing to see how our model has 0 such predictions in that area. It is somewhat similar to a cancer prediction, where the risk of predicting false negative is very much costly compared to the risk of predicting a false positive. A single problem noticed is how the model is completely dependent on only two column contributions, i.e., total bad and total good debt. Now, let's look at the optimal best model that I have chosen, the boosted tree. While rest of the stats remain similar to the bootstrap forest, unlike bootstrap, boosted tree is not completely biased on good and bad debt, making it a better model which would holistically evaluate the customers. It- The problem with Bootstrap is that it's only dependent on two factors, and even losing the data on one of them or unavailability of even of one of them makes the model completely crippled. Now, to demonstrate the problem that is with Bootstrap, I have removed the major two columns, that is the bad and good debt, and reran the simulation. As you can see, this time the AUC has completely fallen down due to the such change. The dependency this time is majorly on job title, experience years, age, and income type. Interesting to see that total income plays very little role compared to the above factors. I reran the model screening for all the other datasets using this method of removing total good and bad debt just to check some of the stats that I would be getting, which might be fascinating compared to the previous ones. As we can see, even now the neural boosted and the boosted tree are the major good models when compared to Bootstrap. And Bootstrap also kind of still perform well after removing the good and bad credit. The misclassification is least for boosted trees, followed by the bootstrap and decision tree. AUC highest for boosted tree, then by bootstrap. RASE is almost similar for all of the highlighted best models. To understand the data better, I use redistribution tree. I optimally split the data to understand which parameters at what point affect my interest target status 0 and combine this with the insights I got commonly from my top best models. And as it can be observed, the total income being in the range of 11 lakh 25,000 and 40 lakh 50,000, and the total income still being 35 lakh and 1,000 income being commercial or associate or pensioner, and the total family members being less than 3, and the applicant gender being M, he has a higher chance of being rejected, which is a bad thing, which will be explained in the further slides in the business use case. And Now, coming to the business insights or the way the companies can use my model. Factors such as applicant gender, total income, income type, education type, and family size play a crucial role in the approval of a credit. Credit card approval determination is much easier if data on the total good and bad debt of an applicant is available. Logistic regression, which is generally used, performs way less when compared to the advanced ML methods, that is machine learning method, especially when decision trees are involved, which is observed in models such as boosted tree and bootstrap forest. As seen, gender in fact is affecting the models being trained. This is bad. This introduces a new problem of discrimination due to the sensitive variable, that is gender. We must ensure such factors should not create bias in our business model. Overall, companies must really take the total bad debt over total good debt into consideration for an applicant for credit card approval.